inviting me to give a talk. By the way, am I audible?
Yes.
Okay. So this talk is actually based on a joint work with my former student Shiva Prasad Barik and my current postdoc Manoj Bhattacharjee. So the essential part of my talk will be the theorem which is known as Commutant Lifting theorem, and I'll tell you shortly what this theorem is all about. So this theorem was first introduced by Donald Sarason in the context of finding an alternative approach to a function theoretic problem, which is known as interpolation problem. So my plan for the rest of this talk is that I'll describe the interpolation problem first, and then I'll tell you how it is connected to the commutant lifting theorem. And then I'll describe some of the classical commutant lifting theorems. And finally, I plan to talk about its generalization in the Schur-Agler class as the title of my talk suggests. So that's the plan. So let me tell you the interpolation problem. So it's called the Nevanlinna-Pick interpolation problem, and it asks that if you take a n number of distinct points in D. So here in this talk, this D always will be referred as the open unit disk. So you take n number of points, Z1 up to Zn, they are all distinct, and you take scalars W1 up to Wn, they could be same, though. Then it asks whether there exists a holomorphic function on D such that this infinity norm is less or equals to 1, meaning that you take the supremum of phi over the open unit disk, and it has to be less or equals to 1. And it interpolates the data, meaning it takes this Zi to these points, to Wi for all I. So that's the problem. And let me tell you that this restriction here, so if you remove this restriction that this infinity norm of phi to be less or equals to 1, if you don't require that, then of course there even you can find a polynomial of degree n minus 1 which actually interpolates this data. In fact, you could take this some well-known interpolation polynomial like Lagrange interpolation polynomial, which will do the job. So things becomes complicated once you put this restriction that the supremum norm of phi to be less or equals to 1. In other words, you are looking for a function which is from D to D closure, and it interpolates. So so this problem actually has a so the solution to this problem is given by this theorem here. It says that so this NP problem has a solution, meaning you will find such an interpolant from D to D closure, which takes Zi to Wi, if and only if you you form this n cross n matrix depending on the data, depending on the points you have given to you, those distinct points Z1 up to Zn and the scalars W1 up to Wn. So this n cross n matrix has to be positive semi-definite. So that's the necessary and sufficient condition to have such an interpolant. So that's a remarkable theorem in the sense that it actually turns this function theoretic problem to a problem of linear algebra. Because it, after all, it actually asks you to check whether this n cross n matrix is positive semi-definite or not. Now, so the function theoretic proof, there is a function theoretic proof which actually based on something called Schur algorithm, which essentially reduce the number of points meaning you start with a number of points, and then it actually reduces the points to a 2 points, and it actually I mean the theorem boils down to whether you can solve the problem for n equals to 2. If you can do that, then using this Schur algorithm, one can solve this endpoint interpolation on the unit disk. And for 2 points, there is a well, it's kind of a well-known theorem in complex analysis probably, which actually tells you what to do if you have 2 points, or what if your n equals to 2. So that's known as Schur-Agler theorem. It tells you that if you have a well, if you are looking for a holomorphic function from D to D, such that it interpolate Z1, Z2 to W1, W2. So we have a pair of points here. Z1 and Z2, they are distinct, and we have W1 and W2. So if I interpolate such a data, if and only if the hyperbolic distance of this W1, W2, so which is the left-hand side of this inequality, has to be less or equals to the hyperbolic distance of this Z1 and Z2. And of course, finally, one has to see that this inequality here, so this hyperbolic minimizing condition is actually equivalent to the corresponding 2x2 peak matrix, or NP matrix is positive semi-definite. That one has to prove, but that's not very difficult though. So that can be proved. And so a particular case of this Schur-Agler theorem, so in particular, if you take this Z1 to be 0 and W1 to be 0, meaning if you are looking for a holomorphic function from disk to disk, which fixes origin, and take Z2 to W2, then so this well, Schwar's lemma actually tells you how the function will look like, right? So a holomorphic function from disk to disk which fixes origin are always look like, well, always satisfy the inequality that modulus of phi z has to be less or equals to modulus of z. That is well known. So in that case, then your modulus of W2 has to be less or equals to mod of Z2, and which is precisely this inequality if you take your Z1 and Z2, Z1 and W1 to be both to be 0. So then this inequality actually boils down to modulus of W2 has to be less or equals to modulus of Z2. So all I'm trying to say here is that if you take Z1 and W1 both to be 0, then it actually boils down to the classical Schwar's lemma that can be used to prove this theorem. And for a general case, if you don't have this Z1 and W1 to be both to be 0, then what you could do is there is a standard trick which well, essentially pre-composing and you compose and pre-compose by some automorphism, some Mobius transformation accordingly, and which will boils down to the case where your Z1 and W1 are both 0. So there is a standard trick which actually reduces to this case, and then one can prove this Schwarz-Agler theorem. So essentially, it's just the slight generalization of the Schwarz lemma, which tells you this theorem. So that's the basic idea of how this function theoretic proof goes for this Nevanlinna-Pick problem theorem. So I'm going to tell you how this operator theoretic approach actually helps you to prove such a theorem. So I mean, by looking at the problem, there is no Hilbert space inside, right? But it's a greatness of Sarason, who actually observed that, well, there is a operator theoretic way one can solve such a problem. So I'm going to describe that. For that, actually, one needs to know what is called something called Hardy space and certain other things. So this Hardy space is actually consists of holomorphic functions on the unit disk, which has a power series expansion like this, ANG power n, such that this coefficient of the power series is actually square summable. That's the requirement you put. That's the condition you put. So in other words, one can actually clearly identify this space H2D with the little L2, that is the space of all square summable sequences, by simply identifying or by sending such a f to its power series coefficient. In this case, it's the sequence an. So you send f to the sequence an. That will define a actually unitary correspondence between this Hardy space to L2, little L2. So if you are not really, if you haven't seen this Hilbert space before, you can think about it as an L2, little L2. Now this Hilbert space is also a reproducing kernel Hilbert space. I'm not really going to define here. I'm going to tell you what is the exact meaning of something being a reproducing kernel Hilbert space, but it has a kernel. So this kernel function is actually implicitly determined the Hilbert space. So, and in this case, the kernel is called the Jacob kernel. It's defined by this 1 upon 1 minus ZW bar. So that's a function in two variable, holomorphic in first variable and anti-holomorphic in the second variable. So now if you fix something on the second variable, that is if you fix a W from the disk, then it becomes a holomorphic function in the first variable. And if you use the simple geometric series expansion of this 1 by 1 over ZW bar, then you will be able to see that as a function of Z by fixing a W, so this function is actually belongs to H2D, meaning that the power series, the coefficient you get in the power series expansion there, and it's square summable. That's actually easy to see. So in particular, what I'm trying to say is that this vector, if you denote this to be kwz, so here w is fixed and I am just varying it, well, it's a function of z. So that's a holomorphic function from this on disk, and it's actually a member of H2D. So this is the fact which I'm going to use, and these are called the kernel function. And on this Hardy space, there is a kind of a distinguished isometry there, which is called the Hardy shift. It's essentially the multiplication by this coordinate function z. It maps f to z times f, essentially multiplied by you just multiply by this coordinate function z, and that can be proved, can be shown to be isometry. In fact, the identification I told you earlier, that this Hardy space is isomorphic to little L2, or unitary equivalent to L2. So under that unitary equivalent, this MZ is actually unitary equivalent to what is known as the right shift or the unilateral shift on this little L2. So that's the isometry you can think about this MZ as the shift on little L2. And this shift has a nice action, or rather adjoint has a nice action on these kernel functions I talked about. So if you take this kernel function at W, that is k sub W, and if you apply this MZ star to it, so it's essentially tells you that these kernel vectors are the eigenfunction of this adjoint of MZ with eigenvalue W bar. So that's a nice property to have, and one can very easily check by simply inner product computation will tell you this, that these are the eigenvector with eigenfunction. Sorry, eigenvectors with eigenvalue W bar. We also need to know what is a coinvariant subspace. We say that if you take a closed subspace of the Hardy space, you say it's coinvariant if it is invariant under the adjoint of MZ, adjoint of this distinguished isometry MZ. So then you say it's a coinvariant subspace, and then well, so by this because these kernel functions are the eigenvector, so therefore you can say that this one-dimensional space generated by, let's say, this case of W, that's a one-dimensional subspace, and that is a co-invariant subspace because it's an eigenvector, right? It's a eigenvector of mg star with eigenvalue W bar, and in fact, instead of taking one such kernel function, you can take finite number of them, and you can take the span of finite number of such kernel functions. So that also will give you some finite dimensional example of some finite dimensional co-invariant subspaces. And also one can define this multiplayer algebra on such a Hilbert space, on such a Hardy space. What is a multiplayer algebra? Well, it actually consists of, again, functions defined on disk, complex valued function, such that if you take any function from the Hardy space, and then if you multiply it by phi, it again has to land on the Hardy space. So phi times f has to be again a member of the Hardy space for all f. So okay, so one thing one could immediately say is that because this Hardy space has this constant function 1, so if you take this f to be the constant function, then it says that phi itself has to be a member of the Hardy space. So therefore, in particular, your phi has to be an analytic function. It has to be an analytic function on the disk, but also it has to be a member of H2D. That is, the power series also has to be square summable, power series expansion of phi. Another thing is that, so because of this fact, it actually induces a operator simply multiplication by this function phi. You just defined a multiplication operator by sending or by mapping f to phi times f. That will define a, I mean, that will be a well-defined operator from Hardy space to Hardy space, and a direct application of closed graph theorem will tell you that such a operator is actually bounded. So given a multiplier phi, one can immediately associate a multiplication operator which will denote by m sub phi. It's like the mz which is defined earlier, just multiply by z. In this case, we will multiply by such a multiplier phi. And that m sub phi will be a bounded operator. And in fact, one can prove that the norm of the bounded operator will be exactly same as the supremum norm of your phi. So so that's something very nice to have. It doesn't, I mean, one may not necessarily always have that. So with respect to this norm, the norm, so therefore you can define a norm on this space of multipliers by borrowing it from the associate multiplication operator, meaning you can define the norm of phi to be the norm of the operator m sub phi. And then it becomes a, in fact, in this case, it's algebra. So it becomes a Banach algebra, and so on. So, and in fact, it turns out that in this case, it's actually this nice Banach algebra, which is denoted, which is called the bounded analytic functions on D. So it's denoted by H infinity D, consists of set of all bounded analytic functions.
And is the norm strictly less than the norm of the Hardy space? This norm, operator norm.
No, the operator norm is same as the supremum norm of phi. On the other hand, the Hardy space norm is defined in a different way. You take the power series and the sum has to be square summable.
Okay.
Okay, so this associated multiplication operator I talked about, they also have there is another way to characterize them. So which also we need this characterization also. So it tells you that if you take a bounded operator on the Hardy space, and if it commutes with this distinguished isometry, the Hardy shift, if it commutes with mz, then these are all operators which are of the form m sub phi, or the associated the multiplication operator associate to a multiplier. In this case, the multipliers are H infinity. on the space of bounded analytic functions. So so this is another way of saying what are those associated multiplication operators are associated to a multiplier. So in fact, so these last two bullet points is actually made the connection with the interpolation problem I talked about. If you remember, so in that interpolation problem, we are actually trying to find a bounded analytic functions. In fact, the norm has to be less or equals to 1. We're trying to find a bounded analytic functions, and and here we have seen that this bounded analytic functions is same as so these bounded analytic functions actually induces a multiplication operator or induces a operator from Hardy space to Hardy space such that the operator has to satisfy has to commute this distinguished isometry MZ. So that's the connection. So instead of finding a bounded analytic function phi is same as you're trying to find a bounded operator on the Hardy space which actually commutes with the MZ. So that's the connection. So that's the connection Sarason observed, and in fact, maybe we do need some other maybe one more property of this associate of this multiplication operator. So you again take a multiplier phi from this H infinity D. So then you look then this associated multiplication operator M sub phi. The adjoint of it also has this similar property which this MZ had. We have seen before that this kernel function are the eigenfunctions or the eigenvector of this operator with eigenvalue phi z bar. So that's the other thing we need. So now let's look at so this NP problem. So this NP problem actually asks you for existence of a phi such that this corresponding multiplication operator M phi as a bounded operator from H to D to H to D is a contraction because we have assumed that this infinity norm is less or equals to 1. So therefore, it has to be a contraction. And if I look at this kernel vectors at those initial data, so remember we had this n number of points Z1 and Z2, Z1, Z2 up to Zn. Those are the distinct points. And we have seen that this M phi star has this nice action. These kernel vectors are the eigenvectors. So therefore, M phi star K sub Z has to be phi Z I bar K Z I for all I up to 1 to n. And because this phi interpolates, phi takes this Zi to Wi, so therefore it has to be Wi bar Kzi. So in particular, we are looking for a bounded operator M sub phi which satisfy, which has such that this M phi star has this nice action on the finite dimensional space generated by these kernel vectors Kzi I equals to 1 to n, and that's a coinvariant subspace which we have seen earlier. So in other words, if we just define this coinvariant subspace Q to be the span of these kernel vectors depending on the data Z1 up to Zn, you consider this coinvariant subspace and then you define a operator X such that its adjoint has the same action as this M phi star has. So then actually we are asking whether this X star has a extension, whether this X star can be extended to define a operator on the whole Hardy space and which look like a adjoint of some M phi star. That's what actually we are looking for. So the fact that the phi interpolates the data is actually captured by this action of M phi star on this kernel vector. In other words, this operator here, X star, has this property that X star takes this Kzi to Wi bar Kzi. So this interpolation is guaranteed. Only thing is that one has to look at whether this operator X star can be extended to the whole Hardy space it's actually initially defined on this finite dimensional subspace, n-dimensional subspace rather, Q. One has to find the extension of this X star on the whole Hardy space, and which has to be of the form some M phi star. So that is same as solving the NP problem. So as I told you, the NP problem has a solution if and only if. So this X, the operator X, has to be a contraction, and so this X star has a extension to a operator Y star. Y has to be a contraction, and Y should satisfy, Y should commute with MZ. Okay, so this Y here, yeah, of course we are looking for so this Y commutes with MZ, meaning that Y has to be some M sub phi. So the characterization we have seen before. Any operator on the whole Hardy space which commutes with MZ are of the form M sub phi for some phi which is coming from the multiplier space. So this identity here, or this commutation relation here, so this identity here actually tells you that Y has to be of the form M sub phi, and Y is a contraction simply tells you that the phi has to be infinity norm of phi is less or equals to 1, and so this Y star is a restriction of Y star is a extension of X star. Actually will tell you that this phi will interpolate the data, will take Zi to Wi. So therefore you are done. So you'll get a phi which will interpolate the data. So now what Sarason proved is that, well, after this, after making this observation that NP problem is equivalent to finding this extension of this operator X star here. So by the way, so whenever I say this Y star is an extension of X star, so it's also same as saying that Y is a coextension of X, or Y is a lift of X. Y is a yeah. So those are the terminology we also use. So Y star is the extension of X star is also same as saying that Y is a coextension of X, or Y is a lift of X. So what Sarason proved is that given such a X, one can always find a lifting Y such that it satisfy such that it's a contraction and it's commute with MZ. So that is the Sarason commutant lifting theorem he proved. So therefore this existence of a Y which commutes and it's a lift of X, so that is guaranteed by this commutant lifting theorem. So then the rest, what you have to check is that whether this X is a contraction or not. And it turns out that, well, by just a direct computation, one could check that this operator X is a contraction if and only if the NP matrix is actually positive semi-definite, or the N cross N matrix positive semi-definite, which was the necessary sufficient condition for to have a solution for this problem. I showed you at the very first slide. So that's how this proof goes using this commutant lifting theorem. So now let me tell you what is exactly the commutant lifting theorem Sarason proved. So for that, one also needs to observe that such a X also satisfy this identity. So this X is also commutes with this compression of MZ. So you take this distinguished isometry MZ and you compress it to this co-invariant subspace. Q is this co-invariant subspace, which is the span of those kernel vectors at Z1 up to Zn. And one can show that this X actually commutes with this compression of MZ. And what Sarason prove is that you take a co-invariant subspace and you take a bounded operator on that co-invariant subspace, which is a contraction, and it commutes with this compression of MZ to Q. Then you can lift this X to get a operator Y acting on the whole Hilbert space, which is the Hardy space here. So you'll get a operator on the bounded operator on the Hardy space, which commute with MZ and which is a lift of X. And in fact, this lifting is a non-preserving process, meaning this co-extension is actually so you'll get a non-preserving lifting. So norm of X also will be same as norm of Y. So that's the commutant lifting theorem which Sarason proved. In fact, it's after nearly 50 years the NP problem was proved. So you can see that it's kind of a, I mean, since it's just a coextension of certain operator which is defined on a co-invariant subspace, so therefore it's kind of a purely operator theoretic. I mean, it's a purely operator theoretic theorem, and therefore it should have certain applications in operator theory. One should expect that, and indeed this is the case. It has certain applications in dilation theory, and also it can be used to prove a theorem like Toeplitz Coronat theorem, etc. So therefore, I mean, that is why people actually try to generalize it. And in fact, immediately after Sarason proved this theorem, Nas actually extended this theorem for arbitrary contraction. So what he did is that he replaced this compression of mz to q by a arbitrary contraction, and he proved just a analogous theorem in that case. So that's probably 1968, just a one just after this. And it turns out that if you take pair of contraction instead of a single contraction is done by Nas and Foyers. So if you take pair of contraction, this theorem doesn't really holds there. So it doesn't really go through for tuples or even pairs. Instead, it has success in the context of different reproducing kernel Hilbert spaces, meaning that you replace this Hardy space by different other reproducing kernel Hilbert spaces on other domains, and there you might prove a theorem of this kind, analogous theorem. And the theorem which is important for us is a commutant lifting theorem on the space which is known as Drury-Arveson space. So let me just simply define it. Let me just define the Hilbert space first. So this is denoted. Okay, so this consists of holomorphic function defined on this Bn. Bn will be the unit ball in Cn. And it's taking its E valued. E is some Hilbert space which is known as the coefficient space. So this H1 BNE is the Hilbert space consists of certain holomorphic function on Bn taking values in E. There is a explicit way one could define this Hilbert space, but I won't really define it explicitly here, but I take the liberty to just define it by saying that it has this kernel. It's a reproducing kernel Hilbert space, and with kernel which is defined, which is written here. I mean, once you know the kernel, then actually the Hilbert space is implicitly defined. So so this Arveson space has this. Oh, by the way, so this Arveson space is actually in many ways it's actually is the correct analog of the Hardy space, and it share actually many properties which Hardy space also has. So in a sense, this is the correct analog of Hardy space in the ball in Cn. Anyway, so that's the Drury-Arveson space, and then this space has a. I mean, one can talk about the multiplier space again. So that's so this multiplier space in this case are the set of all functions which are holomorphic on Bn again, but in this time it's actually taking values. It's an operator valued function. It's a bounded operator from E to E star valued function, so that the reason we take it to be operator valued is the fact that it has to satisfy this property that if you take a f which is coming from this E valued Arveson space, then if you multiply phi times f, if you do this multiplication, then it has to land in this E star valued Arveson space. So that is why this phi, phi has to be this operator valued so that this multiplication makes sense, and at the end this phi f lands in this E star valued Arveson space.
Is there a reason why you took E star? I mean, is it the dual of
Uh,
E?
no, it's not that. It's
It's
just
not, right? Okay,
another
yeah.
Hilbert space, nothing
Yeah,
else.
yeah.
It's not dual.
I got it.
I mean, one could take this E star to be E in fact. So for simplicity, that in that case, then it will be multiplier algebra and so on. Sorry, yeah, correct. So yeah, that's just another coefficient space, nothing else. It's not pre-dual or not dual, nothing that sort. So and again, as before, I mean, in this case also having a phi. Uh, 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 is there a question or? Okay. So so like before, one can also associate a operator corresponding to a multiplier phi. One can define a multiplication operator m sub phi just simply by mapping phi goes to phi times f. And again, one could take the help of direct consequence of closed graph theorem. Will tell you that that also will be a bounded operator from one Arveson space, E valued Arveson space to the E star valued Arveson space. And in this case, the norm of m sub phi is actually not equals to the supreme norm of phi, which was true in the case of disk, in the case of the Hardy space. But in this case, the norm of m sub phi is usually bigger than the supreme norm of phi, and and in fact, this is precisely the reason why in this case the multiplier space is not really identified. It's actually a subspace, yeah, subspace of this bounded holomorphic function on Bn operator valued though. So that is why this P E star is there. So it's a subspace of that. In fact, it's a strict inclusion. One can prove that there are bounded operator valued function which may not necessarily define a may not necessarily be a multiplier on the Drury-Arveson space. That one could um, that and sorry, concrete example can be found. So well, one can actually define a norm on this space by simply defining the norm of phi to be the norm of the multiplier m sub phi, and then this space also will be a Banach space. And one can talk about the unit ball of this Banach space, which we will denote by m sub 1 of this E valued Arveson space to this E star valued Arveson space. So that's the unit ball of this Banach space. And which is known as the Schur-Agler class of function. So this will appear many times. So therefore, we should remember this, that the Schur-Agler class of functions is essentially the unit ball of the multiplier space from E valued Arveson space to E star valued Arveson space. So this is the shorthand notation for S. S is for Schur, A is for Agler. So S is sub n is E star is essentially the Schur-Agler class of function on Bn. So this n reflects the n-dimensional, or sorry, the unit ball in Cn we are in, and these coefficient space are also included in this notation to tell you that we are talking about multiplier from E valued Arveson space to E star valued Arveson space. So now the okay, so it's again after 30 years probably. So the Sarason Commutant Lifting theorem was proved probably around 67. Now this is again in 2001. Ball, Trent, and Vinnikov, they proved this Commutant Lifting theorem in this Drury-Arveson space, and they showed that if you take these two co-invariant subspaces, by the way, again, this co-invariant subspace, you can take them to be same. There is no issue there. Earlier, it was same. Now here I have taken they to be different, but you can take them same. So if you take co-invariant subspaces Q1 and Q2 of these two different Drury-Arveson space, and if you take a bounded operator from Q1 and Q2, which satisfy or which commutes with this, sorry, it's not commute because this Q1 and Q2 are different, so therefore it intertwines actually. So it intertwines with this compression of mgi, So here we are in n-dimensional space. So there are n number of coordinate functions. So these are the multiplication by this coordinate function gi are there. There are n number of them, and it x actually intertwines with all of them. Then, like before, you will be able to find a lift. You will be able to find a lift of x to get a multiplication operator by phi, and phi has to be because x is a contraction. You require your phi to be a contractive. Well, the operator m sub phi has to be a contraction, which is same as saying that your phi has to should come from the Schur-Agler class. And of course, it's a non-preserving lifting. So norm of x has to be norm of m psi. So it's just analogous as before, but the only difference is that it's kind of an intertwining lifting theorem, because I have taken this Q1 and Q2 to be different. But as I said, you can take Q1 and Q2 to be same. So then it will be exactly the Commutant Lifting theorem which we discussed earlier. So in fact, this is slightly, although this Commutant Lifting theorem and intertwining lifting theorem, they are actually related to each other. If you can prove one, you can also prove the other, and vice versa. So they are kind of same. So now what we are trying to do here is that we are trying to, we'll try to generalize again this theorem for something called weighted Bergman spaces. So let me just quickly define what is this weighted Bergman space R. So again, I'll define it by saying what is the kernel is. So we'll use the similar notation which was used before for Arveson space. So in the case of Arveson space, you remember the kernel was 1 upon 1 minus inner product of Z and W, but in this case there is a power here. M is there, so that's actually creates some weights. This is the kernel of this Hilbert space, and if you take, in particular, if you take m equals to 1, then you'll get back the Drury-Arveson space which we have seen earlier. So in this, on this space, again, one can talk about the multiplayer space, and one can talk about the unit ball of the multiplayer space, which is this M1 of these two different weighted Bergman spaces. One is E valued, another one is E star valued. And it turns out that this Schur-Agler class of functions, they are actually inside. So this Schur-Agler class of functions are always defines a multiplication operator from this weighted E-valued weighted Bergman space to E star valued weighted Bergman space. So that is another fact which I am going to use here. So now the problem which we are looking at is the following. So now you take two different co-invariant subspaces Q1 and Q2. One is from E-valued weighted Bergman space. Another one is a subspace of E star valued weighted Bergman space. And again, as before, you take a bounded operator X from Q1 and Q2, which is a contraction such that it again intertwines with this compression of this coordinate multiplication operators. So then the question is, can you find a necessary and sufficient condition for so that this X has a lift? X can be lifted to some m sub phi, where phi is coming from a Schur-Agler class of function. So the reason why I said well, there are reasons to believe that such a thing is not always possible. So that is why I phrase this as finding what is the necessary and sufficient condition for that to hold, for there to exist such a Schur-Agler function which is a lift of your X. So now one thing to notice here is that, as I said earlier, this Schur-Agler class of functions may not be necessarily the whole unit ball of the multiplayer space in this case, because it can be a strict. It can be a strict inclusion. So therefore we are actually putting certain restriction by requiring that the lift should come from the Schur-Agler class. but we'll see that that it not a big restriction. So in fact, one could immediately see that if you take m equals to 1 here, then this weighted Bergman space is the Drury-Arveson space, and in that case, by definition, so this becomes a equality. I mean, the Schur-Agler class and the unit ball of the multiplier space are the same by definition. So for m equals to 1, there is no restriction we are putting. Similarly, if you take n equals to 1, then you are on the unit disk. Your unit ball becomes the unit disk. In that case, also. In that case, also the multiplier space becomes the H infinity, and the unit ball becomes is same as the Schur-Agler function. So therefore, there are no restrictions. So in certain cases, in particular, if you take m equals to 1 or n equals to 1, then there is no restriction. Otherwise, we are of course putting certain restriction, and there are reasons why we are looking at lifting in this class, in the Schur-Agler class. I'll tell you in a minute. But suppose for the time being that we solve this problem for for all m and n, and suppose we find a necessary and sufficient condition, then let's see what we can say out of it. So as you have seen, if you take m and n both are equals to 1, so in this case, you are on the Hardy space, and therefore, so it will recover the Sarason's Commuting Lifting theorem, which we talked about. And in this case, there is no restriction because the Schur-Agler class is same as the unit ball of the multiplier space. So therefore, there won't be any restriction. So you will recover the Sarason's theorem in case of m equals to 1 and n equals to 1. And if you take m equals to 1 and n is bigger, so then these weighted Bergman spaces are the Drury-Arveson space. So therefore, you will recover the theorem of Ball-Trent-Benikoff. And in fact, as it turns out that we not only recover their theorem, we also find a new, I should say much nicer, much cleaner and a simpler proof of these classicals commuting lifting theorem along with a explicit description of the lifting. So and also if you take n equals to 1, that is you are on the unit disk, and if you take m bigger or equals to 2, then you are on the weighted Bergman space or weighted Bergman space on the disk or the usual Bergman space on the disk. So in that case, it was known before that this commuting lifting theorem hold, but the norm of the lifting may not be necessarily the same as the underlying operator. So the norm usually gets bigger. So, but this theorem here actually tells you that when a contraction can be lifted to a contraction, again in terms of putting some necessary. Sorry, if we solve this problem, then it will give you some necessary sufficient condition for a contraction to have a contractive lifting in the case of Bergman space. Needless to say that in all other cases, when your n and m are not any one of these, then of course it gives you some necessary sufficient condition for having a lifting in the Schur-Agler class. So that goes without saying. So now let me tell you the theorem which we proved. Now to describe that, we need to define certain completely positive map corresponding to a tuple of operators. Suppose you have a tuple of operator T1 up to Tn on H, then one can define the sigma sub T, which is a completely positive map from BH to BH, which is just defined by taking the sum of the conjugation. So conjugation by Ti. So that's a CP map, completely positive map. Anyway, so this is the map how it is defined. Then this is the theorem. Again, you take Q1, Q2 two coinvariant subspaces and a bounded operator, which intertwines the compression. So those are there. Those were there before. So then you'll be able to find a lift of such a X. You'll be able to find a lifting of X as m sub phi for a phi which is coming from the Schur-Agler class. If and only if this X has to satisfy certain positivity relation here, which is given, which is displayed here. In terms of this operator tuple S, and S is the compression of this MZI again, compression of MZI to this Q. Anyway, so it has to satisfy this certain positivity. So now, okay, so let me tell you this positivity about this positivity a little bit. So if you take m equals to 1, then you see this I minus sigma s goes away because it's the power is 0. So therefore it requires that one identity minus x star has to be positive, but we have already started with a x which is a contraction. So therefore it automatically satisfies the hypothesis. So if you take m equals to 1 in particular, then the hypothesis is, so this hypothesis becomes trivial. So any contraction then can be lifted to the Schur-Agler class. And you remember, so if you take m equals to 1, then you are either in the Arveson space or in the Hardy space, right? So, and we have seen the Commuting Lifting theorem before where we didn't have any restriction on x. Any contraction can be lifted. So this is kind of consistent to that. So by taking m equals to 1, you will get back those theorems. So let me tell you that if you take m equals to 2 here and suppose n equals to 1, then this condition, this positivity as the necessary sufficient condition here simply turns out to be this positivity, which is I guess I believe it's actually well known to operator theorists. In fact, it's called the Jacob positivity of this pair S and X. So these are the positivity. This type of positivity is kind of standard and very well known. So anyway, so I think I don't really have how much time I have, Jyotsarov?
You can take 5 more minutes. It's fine. It's
Okay.
5:56. So
Okay.
we are well.
Okay, fine. So okay. So all right. So just let me briefly give you some ideas how to prove such a theorem. And as I said, that this actually gives you a much cleaner proof for even for this classical proof of these classical theorems. So therefore, let me tell you where it differs from the existing proof and so on. So let me give you some ideas. So I'm not really going to tell you if you have a lifting, then the necessary condition is actually kind of inherited from these weighted Bergman spaces and so on. So this is that part is some sort of easy, so that I'm going to avoid. So what I'm trying to show here is that suppose you have a x which satisfy this necessary sufficient condition, then how do you find this lifting? How do you find this phi? So so this is the part which I am going to tell you how to find this phi. So for that, one need to know this this again a non-trivial theorem which tells you that if you after all we are looking for a phi which is in the Schur-Agler class, and it's in fact so so there is a result which tells you that any Schur-Agler class of functions is actually related to a unitary and it actually transfer function of a unitary. So phi has to be given by certain formula which is written here. So anyway, so you don't really look at this formula. I mean, so if you haven't seen this formula before, then it might look complicated.
Bhattacharjee,
Yeah.
I have a quick question. Do you really mean K to Kn?
Yes. We do because I think in this case probably your
Yeah, Z is the row operator, so that's why to otherwise.
Something like that is okay. Yeah.
correct. Z is Z1 identity or Zn identity, something like that.
So what is the definition of Schur-Agler class? Is it precisely those which have this realization formula?
It's not actually. I told you so. These Schur-Agler class functions are is the unit ball of this multiplier space of the Arveson space, corresponding Arveson spaces. So that's the definition.
Unit ball.
Yeah.
Okay. Fine.
Okay. So you don't really look at this how it is related to the unitary, but think about for a moment. So even if you take n equals to 1 here, this Schur-Agler class is actually becomes the, and in fact you take this e and e star to be the complex numbers. So then this becomes the bounded analytic functions. So it essentially tells you that if you take a bounded analytic functions whose norm is less or equals to 1, then it has to be something like this. So I mean, there is no a priori reason to believe that. Believe that it's related to a unitary like this. So that is why it's kind of a non-trivial theorem. And you see, I mean, you see, sometimes, I mean, if you have a bounded analytic, a holomorphic function which is bounded, so and you want to find certain other properties of phi. So this boundedness and the analyticness may not be necessarily good enough. So maybe so therefore, so a expression like this or this phi has this realization might help you. In fact, in this case, we'll show that, okay, because we are after all, we have to find a phi which is in the Schur-Agler class. So therefore, so this fact here actually tells you that, well, why don't you just look for a unitary whose transfer function is exactly phi? So therefore, all it boils down to finding a unitary whose transfer function is this phi. So I mean, this theorem is kind of a non-trivial and has many applications even in function theory and also, of course, in operator theory. So okay, so let me go on. And then there is the identity. So this operator identity also played a crucial role here. This operator identity involves this defect operator of S, T, and this operator which appears as the positivity of the operator which is the necessary sufficient condition. So okay, so even it becomes simpler if we take m and n equals to 1. So it boils down to this identity, operator identity, which can be checked very easily. In fact, a simple computation will tell you, and you use the fact that this x actually intertwines with s and t. So then you will see that this is kind of immediate. So now, if you believe that such a operator identity is true, now having such an identity, one can immediately define an induced isometry on appropriate spaces. Well, because this V is an isometry that one can check very easily. In fact, if you look at the norm square of such a vector, it will give you the left-hand side of this operator identity applied to F inner product with F. Similarly, if you look at the inner product of this vector here on the right-hand side, it will give you the operator which appears on the right-hand side applied to F inner product with F. So this isometric property can be checked very easily. And once you have isometry, it is also very standard that you might have to add a Hilbert space to extend it to a unitary. So you just add possibly a infinite dimensional Hilbert space so that it becomes a unitary on appropriate Hilbert spaces. And then you take the transfer function of phi, which I just told you in the previous slide. You take the transfer function of this unitary and you show that requires a little bit of work to show that this transfer function actually lifts the operator x, which we are looking at. So that's the idea of the proof. So these ideas are very similar, very classical. Many people have used it. So what is different here is that this operator identity also people have noticed earlier, but it is slightly different than that. Maybe there is something new, but the important point here is that, well, this transfer function, I mean, so once you find this unitary, the transfer function is the one which will lift the operator x. The proof of this fact actually is much simpler. We found a better proof and a simpler proof, which tells you that this transfer function is actually a lifting of x. So that's how the proof goes, and I think here. So here are some references. So the content of this talk can be found in this first article here. And Sarason proved Sarason's commuting lifting theorem can be found in this paper. And similarly, the commuting lifting theorem of Ball, Trent, and Vinnikov can be found in this third article. So thank you very much.